Baryon asymmetry is one of the biggest unsolved problems in modern physics. It refers to the apparent imbalance in the universe between baryons, particles made of three quarks, such as protons and neutrons, and their antimatter counterparts, antibaryons. This asymmetry is a fundamental issue in cosmology, as it implies that there was a violation of the principle of CP, charge conjugation and parity symmetry, in the early universe. The CP violation refers to the fact that the laws of physics are not the same for matter and antimatter. In theory, matter and antimatter should have been created in equal amounts during the Big Bang. However, the observable universe is almost entirely composed of matter, with very little antimatter. The question of why this is the case is one of the most intriguing puzzles in modern physics. One possible explanation for the baryon asymmetry is the idea of baryogenesis. This theory proposes that the universe underwent a phase transition in its early stages, during which the CP symmetry was broken. This would have led to an excess of baryons over antibaryons, as the baryons were preferentially produced over their antimatter counterparts. There are several models of baryogenesis, such as electroweak baryogenesis, which involve the interactions of the weak nuclear force with other fundamental forces. Another possible explanation for the baryon asymmetry is leptogenesis. This theory proposes that the asymmetry was created in the decays of heavy particles called leptons. According to this theory, the universe initially had equal amounts of leptons and antileptons, but a CP violation in the decay of heavy leptons led to an excess of leptons over antileptons, which in turn led to an excess of baryons over antibaryons. This theory is supported by observations of the cosmic microwave background radiation, which suggest that the universe was initially very homogeneous. Despite the many proposed explanations for the baryon asymmetry, the problem remains unsolved. The CP violation required to generate the asymmetry is much larger than what is predicted by the standard model of particle physics, which describes the behavior of fundamental particles and their interactions. Therefore, physicists are searching for new physics beyond the standard model that could account for the baryon asymmetry. Experimental efforts to study the baryon asymmetry include studies of the behavior of the weak nuclear force, which is responsible for the decay of particles such as protons and neutrons. The weak force violates CP symmetry, and studying its behavior could provide insights into the origin of the baryon asymmetry. The Large Hadron Collider, LHC, a particle accelerator located at CERN in Switzerland, is also being used to study the behavior of fundamental particles and their interactions, with the aim of uncovering new physics beyond the standard model. In addition to experimental efforts, theoretical physicists are also working to develop new models of bariogenesis and leptogenesis that could account for the observed baryon asymmetry. These models involve complex mathematical calculations and are often tested using computer simulations. In conclusion, the baryon asymmetry is a major unsolved problem in modern physics, with implications for our understanding of the early universe and the behavior of fundamental particles. While several theories have been proposed to explain the asymmetry, the problem remains unsolved, and physicists are continuing to search for new physics beyond the standard model that could account for it. Through experimental and theoretical efforts, we hope to gain a better understanding of the origins of the baryon asymmetry in the universe. Don't forget to like the video and subscribe to the Pinfography YouTube channel.